So it turns out that you actually end up seeing something that looks like an interference pattern from just a single slit. So how could that possibly be? If you think about Young's double slit experiment, it's the light from the upper open slit that's interfering with the light from the lower slit. But here, if I just have light coming in and I'm trying to block it out, and some of it gets through, so we'll think about Huygens wavelets when we do this. How on earth could I end up with a pattern that has bright and dark fringes? So I'll denote what people see, and you guys will see some nicer pictures after this, after our theoretical treatment. So this would be the intensity on a screen. So this would be what's called the central bright fringe, and then these would be the first order dark fringes. And this obviously would be the central bright fringe. So this is pretty perplexing, and I don't know how long this stumped people, but the answer actually is an old answer, is that if you think about the Huygens wavelets, you realize that actually what I really have is every time I have light coming through something like this, so this slit is not infinitely thin, it has some size d, so we'll write that on there using Giancali's kind of awkward notation of big D, is that really what I have is I have a Huygens wavelet here, and then underneath it I have another one. And underneath that I have yet another one, and underneath that I have yet another one, and so on and so forth. And I'll just denote a couple of them. And so even in a single slit, if the single slit is of non-zero size, so it's got some appreciable width itself, is that the light from the top of the slit could possibly be interfering with the light from the bottom of the slit or the light from the middle of the slit. And it turns out that's exactly the description that we need to come up with a formula for single slit diffraction. And I'll just sketch out the argument and give the primary result for the central bright fringe, and then leave the rest of the details for anybody who's truly interested. So let me just pick some wavelets, and I'll denote them with these colored Lucky Charms. So the right way of pairing stuff is to realize that when I have a single slit, I can kind of make a fake double slit out of it by pairing the light from the top of the slit, in this case that blue dot, with the light from the middle of the slit. So here we have basically two slits. Each one is not of total width d, but d over 2 and d over 2. And then what I can think about is the light coming from here and here. They're going to double slit. And the light from here and here, they're going to double slit. And I can pair them off that way and basically just reuse my formula that I've already derived for double slit interference. So let's figure out where the first dark fringe is. So what these are not one, but a huge, actually infinite collection of pairs of rays of light that are separated by d over 2. And if I have destructive interference, which is exactly what's happening here, clearly a dark spot would be destructive interference, I have delta r in between these, which is the distance in between them. Because we had to split the slit in half to pair them up, the distance in between them is not d, but d over 2 sine theta times m lambda. So in this case, lambda is the, so distance in between them, and then lambda over 2, so 1/2 lambda for the first dark fringe. Right. Yeah, perfect. So the geometric result is that d over 2 sine theta, that's the extra distance that, for instance, this has traveled. D over 2, because we had to split the slit in half. Sine theta, that's delta r. And when that's equal to lambda over 2, then we get the first order destructive peak. 2's go away, and what we end up with is d sine theta equals lambda for first dark spot. So that would be the dark spot above. For the dark spot below, we would have a minus. The way that you pair them to get the next dark spot and the next dark spot is a little bit kind of clever and obscure. What you have to do is you've got to split the halves into halves and the halves into halves. So to get the second order dark spot, I'll just write it up really quickly, and you could convince yourself of this. You don't need to know it, but maybe somebody's a proof aficionado out there. So for the second order, I would be pairing two slits, each of d over 4, so I'd split the halves in halves, sine theta. So that would be the geometric distance that that lower wavelet would have to travel versus the upper one. And then again, that would be equal to lambda over 2 because I want to make them destructively interfere. So the interesting thing about this is the dark spots are always characterized by 1/2 wavelength difference, but the 1/2 wavelength is different parts of the slit interfering with other different parts of the slit. So this is actually characterized by the light from the top half interfering destructively with light from the bottom half. This is characterized by light from each quarter of the slit destructively interfering with the next quarter of the slit, but it's always the first order interference, destructive interference, it's always lambda over 2. And so the general formula would be delta R, path length difference is d over 2 to the n sine theta equals lambda over 2. So in general, what you get is the location of the mth order interference pattern. Sorry, that's 2m. Called it m, keep calling it m. Is d sine theta equals m lambda, which looks a lot like the location of the bright fringes for the double slit interference pattern, but it's not. These are the dark fringes. And it's still true that m is positive or negative integers. The other difference in this case is that we don't have 0. So the central bright fringe is, as the name suggests, bright. Right. So it's a funky argument, but the important thing is that this weird thing with the Huygens wavelets actually has finally paid some dividends for us when we get to diffraction. So it explains why things diffract, why they bend when they go around corners, and why we end up with a single slit what seems to be destructive interference. Okay, so let's have an actual problem with this. And you'll get to see the piece of math that you get to use very frequently to save yourself some time. So let's say that we have some red light. And it shines on a single slit of weirdly precise width. 42.5, that's a mu, so that's microns, so 10 to the minus 6 millionths of a meter. And we can ask 2 questions. So first question is, what's the angular size of the central bright fringe? And usually what this is called is the central peak. So this is the central bright fringe or central peak. And the second question we can ask is, how big is it? And this is a question that's kind of related to the angular magnification. And I mumbled some things about tangents and small angles. This is when we'll actually see them in practice. Okay. So I'll keep this up, but erase all the clutter. So this is the angular size of the central bright fringe. So right across from the slit itself, this is the center. And this angular size is actually this entire angle. We'll call it, how about beta? I haven't used beta for a while. And then the actual size, we'll call this delta y because it's oriented in the xy plane upwards, so that's fine. Y is good. Okay. And I'm going to write down this formula so I know that d sine theta, because we always formula hunt first. So this is the first dark spot. The first dark spot ends the central bright peak, so that's lambda. And I'm told what d is. I'm told what lambda is. So really, that just directly gives me sine theta. That's really nice. The question is what does theta have to do with beta? Okay. So theta is actually this angle. So what this is going to tell me, so this is the angular distance from directly across to the first dark fringe. And then there's going to be a symmetric angle down here. Technically, if we wanted to find that, we would have to do that. So that's where the upper path length is longer than the lower path length. So the -1, m equals -1 fringe. But it's going to be the same number. It's symmetric. We don't have to bother solving it. Okay, so the rest is just an exercise in units. So I have sine theta is 680 nanometers divided by 42.5 microns. So that's 680 times 10 to the -9 meters over 42.5 times 10 to the -6 meters. So this looks like it's going to be small. I have a calculator, beep, boop, boop. And my calculator will return either radians or degrees, whatever I ask it to. Let's say it returns degrees. So theta is 0.917 degrees. So that means this beta angle would be twice that. 1.83. Sure. 3 sig figs is good. Okay. So that's the angular size of the central peak. So don't forget that this is from m equals 1 from the center line. This is what that theta is telling you. And then for the second dark fringe where you would use 2 there, that would get you from the center line to there. So that would be theta. So the width of the angular size of this would be twice that. Okay. So A. Okay, what about B? How big is it on the screen? So how big is this thing? And the reason people keep track of this is that, my picture aside, most of the light, I'll show you a couple of these, most of the light actually shows up in that first bead. So most of the photons, if you're doing astronomy, for instance, will be there. This also characterizes how much the light smooshes out, right? So if I was looking at a star, which is like really teeny tiny, and I pass it through a single slit, namely the aperture of a telescope, it's actually going to smush out by this amount. And I want to keep track of that too. So that's basically the effective size of how much this is smushed out. Okay, I'll keep that because I want it. Okay, so B, what is the actual size? So this is where the small angle approximation is useful. You can really use it depending on how much you care about the precision of your answer. So this is kind of a glib answer, but when theta is, like 15 or less, it's okay. At least in this class. We have an angle that's 2 degrees, so we're like completely justified in using the small angle approximation. And what the small angle approximation essentially says is that all of these things can be treated the same. Theta, sine theta, tan theta. So if you've been through the calculus sequence, the justification for this is essentially all of these things these two things have theta as the first term in its Taylor expansion. So it's basically like a Taylor series argument. Okay, this is okay with one giant caveat. radians are the natural unit for things that show up inside sine and tangent as mathematical functions, right? And so this is because it depends on power series expansion or Taylor's theorem. This is really a mathematical property of these. So you can't do this in degrees. Absolutely doesn't work in degrees. This is radians only. So what we have to do is we've got to change this and turn it into radians instead. So I'm going to redraw this diagram and just simplify it a bit. So I've got delta y on this side, and then I've got L, distance in between this and this, and I've got beta. And the idea is that if you imagine this is much smaller than that, so maybe that's actually worth drawing in a little bit more precision. So here's delta y, and this is a really long distance in between them. This is the equivalent of saying beta is small. So beta is small when delta y is small compared to L. So the other smoking gun that I get to use, the small angle approximation, is that when this is small, this is small. Okay, so now what I can do is, not bother myself with arc tangent or an arc sine, or even trying to figure out where, if anywhere, these right angles should be. I'll just say that this is, the correct relationship. So beta is tan theta is sine beta, and honestly, that's approximately equal to delta y over L itself. Okay, provided I do this in radians. So beta has got to be in radians for this trick to work. So I've got 1.83 degrees. I've got to convert that into radians. So I'll multiply by pi, divide by 180 degrees, degrees gone. And I know that this is 2 meters. I'm going to guess that centimeters is probably a better unit. So I'll just turn that into centimeters right there. Poof. And then math happens, and I get delta y. The size of this on the screen is equal to whatever I wrote. 6.4 centimeters. Okay, and this is the part where I can, after the fact, justify the small angle approximation, is that, yeah, 200 divided by 6 is pretty small, right? We knew it was going to be fine because the 1.83 degrees is much less than 15. So this is something you'll see a lot. If you get an angle that's 40 degrees or something like that, you've really got to figure out, what trig function to use. Specifically, the trig function that you would have to use if you didn't have the small angle approximation would be this is L and this is delta y over 2, and then that's theta. So you'd have to use an arc tangent. But it's, for us, it's all good. Small angle, that's great. Okay, so let me quickly show you what these things look like in actual real life. So here's an optics track with a double slit complex on it. So there's a green diode laser, and then there's a battery of slits. And we'll just turn it on and see what happens. Okay. Oh, sorry, this is a red laser. So there you can see I've got a bunch of different options for the slits, and then we can zoom in on the actual dot itself. It's kind of hard to tell if it's coming through on this. But you should be able to see, at least by my reckoning, a couple of beads of light. So I see the central bright fringe, and then I see a couple on the other side. I'll kill some light, so hopefully that's a little bit more distinct. Okay, and if you remember how, oh yeah, I can see that really good. So this would be the central bright fringe, and then the first and second and third order peaks. And it can probably do a better job of focusing if we give it something to focus on. There we go. So this is actually a variable slit width, and I can change the variable slit width. So as the single slit gets narrower and narrower, the central bright fringe is going to get wider and wider. So you can think about that in the formula itself as d gets small, theta's got to get big at a fixed wavelength. So the right-hand side of that equation is constant, which means that as one term on the left-hand side gets bigger, the other one's got to get smaller. Okay, and since we're here, let me just show off single versus double slits. So yeah, there's some other cool stuff on the slit mask. So what you're missing out on by not being in lab. So here's side by side a single and a double slit. And on this side, I've got a single slit. On that side, I've got a double slit. So in fact, for a real honest-to-goodness double slit, because each of the individual slits in the double slit, the upper and the lower one, have a finite width themselves, they'll also experience this single slit diffraction pattern. So I'll post some really nice pictures and videos online to accompany this.